All right, question 3.19. We're asked to determine whether some given matrices are singular or not. Now, if you look up the definition of what it means for a matrix to be singular and multiple different books or online, you might get multiple different answers because there are different ways of looking at it. So I was going to go back and let's check out the definition that our book uses. All these definitions are equivalent, but they don't sound the same at first. So I look at our book and its definition 3.11. The definition states a square matrix, so we're only talking about square matrices, same size, n by n, is non-singular if it is the matrix of coefficients of a homogeneous system with a unique solution. So it's non-singular if it is the matrix of coefficients. Okay, so what do we mean a matrix of coefficients? Well, the book uses these as a couple examples. Let me see. Let me just use this one right here. If I think of this one as a matrix of coefficients, what am I thinking of? Well, I'm thinking of 1 times x plus 2 times y and 3 times x plus 4 times y. And homogeneous means we have zeros on the other side. So we say that a matrix is non-singular. Now remember, the book does point this out, and I think it's really good that it points this out. A singular event we think of as a rare event, unusual event almost unimaginable. So non-singular is sort of the way we almost always would expect it to occur naturally, or in the vast, vast, vast majority of times. So it says here it's non-singular if the matrix of coefficients, if it is the matrix of coefficients of a homogeneous system with a unique solution. So not no solution and not an infinite number of solutions, but a unique solution. Now, how can we tell this has a unique solution? I suppose the most straightforward way would be to solve it. And you can do that and see if it has a unique solution. There are other ways, and we're going to talk about them as we go along, but he also uses this as an example. So these two are from example 3.12 of the book. You may or may not notice, but take a look at it for a second, that if you multiply this by 2, you get this, and this by 2, you get this, and this by 3, you get this, and this by 3, you get this. But most importantly, this row and this row are the same row. Now, what would that mean in terms of a system of equations? Well, I'll leave the 1, 2 alone, 3, and we'll just make this a 6 here. And what does that mean in terms of equations? Well, it means they are the same equation. So right here, we really don't have 2 equations and 2 unknowns. We have 1 equation and 1 unknown. And given the format of this equation, it's clear to us that this represents or generates a straight line, and there are an infinite number of solutions. So if there's no solution or an infinite number of solutions, we'll say the matrix is singular. So let me go down to question 3.19. Let's see what that has to say, or rather what it asks us to do. So I'm scrolling down here to 3.19. And the question states or asks, one is singular while the other, there's 2 matrices. One is non-singular. I'm having trouble reading. One is non-singular while the other is singular. Which is which? So let me write down the 2 matrices here. So there's matrix A, and matrix B is 1, 3, 4, 12. And well, your thought is probably, this looks too easy. I don't understand. The question seems too easy. Maybe I'm not understanding it. Well, this is a multiple of this. This row is a multiple of this row. So this matrix is singular. I don't see that happening here. Now, if we want it to be maybe, I don't know, absolutely sure, to confirm what we said, non-singular, singular, we could set up the system, the homogeneous system of equations determined by both these matrices and solve them. And what we would see is that we would get a unique solution here and an infinite number of solutions here. Okay, so that's 3.19 and a nice, short, quick video.